Someone say Medina.
Okay, it is 8:30. I have less people today. Weekends hiding back there. Are they back there? I don't see anyone. Do you? Oh, you are hiding. Alright, so we are missing a few people today, but hopefully they are able to watch the lecture to do the homework on Friday. Because I know at least you three are good with the binary hex and but I think you two needed the lecture anyway, so we should do the lecture. All right, so numbering systems. So the first numbering system that we are going to go over is binary. And one thing that you should know before we go into binary is that pretty much all of these numbering systems have the same format. It's just the base or the number of digits are different. So in decimal, what we're used to, we're base 10, right? We have 10 digits, 0 through 9. And what we do to figure out what the number is for the ones place, we multiply it by 1. For the tens place, we multiply it by 10. For the hundreds place, we multiply it by 100. So like here, we have 9 times 100, 0 times 10, 0 times 1. We get 900 total. But for other number systems, this format is the exact same, except now we have a different number of digits. So in binary, there's only 2 digits, 0 and 1. So our base is in base 2. So the first digit is the exact same. We just multiply it by 1 because 2 to the 0, 10 to the 0, anything to the 0 power is just 1, right? So we get 0 here because 0 times 1. But then in the second place, it's multiplied by 2 because now it's 2 to the power of 1. So we get a 2 here because 1 times 2. And then the third digit is 4 because it's 2 to the power of 2. Now we do 0 times 4. And then the fourth digit is 2 to the power of 3, which is 8. So 1 times 8. So 1 times 8 is 8. 0 times 4 is 0. Plus 1 times 2 is 2. So this is 10. Because again, 0 times 1 is 0. So for those of us new to binary, does that make sense? Yeah.
So you're saying that you kind of just take the number that's at the top, so the list of 0 and 1s are the set that you put to the power 2, and then as you go to the left, it increases by 2 every time. So like 1, 2,
Yeah.
4, 8.
Yeah. So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4 would be over here. Just like we do here, this is 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. So it's something that you've done for almost your entire life. It's just now we have a different base. All right. So if we are going to put it into a mathematical formula, this is what it would look like, right? The number at the digit place times the base, in this case it's 2, to the power of that digit place. So starting at 0, going to however many digits you need for the number that you're representing. And it just comes out to this summation. So this can look scary, but again, it's just a very simple summation with the base. So here's another example. one thing that is very simple, just like if you have a number in decimal and it's all leading zeros, you don't really care about any leading zeros, right? They don't mean anything because it's just going to multiply their base by 0. So we can just start all the way until we see the first real digits. So this is the fourth digit. So it's 1 times 2 to the power of 3. So this gives us 8. 0 times 2 to the power of 2. 1 times 2 to the power of 1. So 8 plus 2, we're 10. And now 1 times 2 to the power of 0, which is 1. So this is 11. 8, 0, 2, 1, which is 11. And you'll often see the base denoted as this subscript. So 11 in base 10, but it's 1, 0, 1, 1 in base 2. So if you want to talk about the range of unsigned integers that you can denote in pretty much any base, like it's very easy for us. If you have 3 decimal digits, it's 0 through 999, right? But that's really just 10 to the third power, which is 1,000 minus 1, 999, right? But it's the same thing for binary. Now we're 0 to 2 to the number of digits that we have. So say we have 4 digits. 2 to the 4 would be 16 minus 1. We would be able to represent 0 through 15. So if we have 16 bits, we're 0 through 65,535. So this is unsigned binary integers. Here are some more examples. What is this number? Those of you that are new to binary, please tell me this number in decimal. Yeah. This is 12. Yes. 8 plus 4 is 12. This number? You don't have to raise your hand. You can just say the answer. Yeah. This is 27. This is 16 plus 8 plus 2 plus 1. And then, like we talked about, a whole bunch of leading zeros. So we see these last 4, same as these last 4. So this one is still 12, right? And now if we wanted to convert from decimal to binary, we're given 7 in decimal. What would this be in binary?
Would it be 0, 1, 1, 1?
Yeah, 1, 1, 1. So we have a 4, a 2, a 1. And for the process of converting from decimal to binary, it's find the largest power of 2 that is smaller. So in this case, it's 2 to the 2, which is 4, because 8 is too much, right? And then once you have that, you put a 1 in that digits place, and then you subtract 4 from 7, and now you need 3 left over. So now 2 to the 1 is the largest that fits. Put a 1 there. 3 minus 2, I need 1 more, so I just need 1, because 2 to the 0 is 1. So 23. Anyone have this yet? I know you know this at this point. So anyone else?
One, zero, one, one, one.
Yes. So we got 116, and then we need 7 left, and we have 7 right here for us, right? So 16, 0, 1, 1, 1. And this is a 4, a 2, and a 1. All right, so we can extend this to go beyond just integers. We can do now fixed point numbers. So if we want to represent fractions, I'm going to go through this more quickly because it's just an extension of what you just learned. And I'm not going to be asking you to do this. If you're ever asked to do this in the future, you have these slides to refer back to. You're basically going to have an integer part and a fractional part, just like in decimal. And you just denote where it turns into a fraction with a decimal point. And just like we do in decimal, once you go past the decimal points, now you're going into the negative powers. So that's our fractional part. So our example is 7.75. The decimal parts is very easy, right? We just went over this. We need 7, so 0, 1, 1, 1. And then the fractional part is a little bit more tricky, but again, it's the same formats. So 2 to the negative 1 is just 1 over 2, right? Which is 0.5, so we need 1.5. So we put a 1 here. And then 2 to the negative 2 is 1 over 4, which is 0.25. So we need 0.25 as well. And then if we have 0.5 plus 0.25, we get 0.75. So this I'm not going to go through as quickly because this is something that I might ask you to do later on, as well as it's important to know in embedded systems, because oftentimes you are going to use signed numbers. So we need a way to represent signed numbers in binary, and the format that we use and the standard that we use is called 2's complement. And again, here is an equation for this, but I am going to kind of just explain through it rather than go bit by bit on this equation. So the most significant bit of the 2's complement representation is going to tell you what the sign is. So if it's 1, you know it's a negative number. If the most significant bit is a 0, you know it's not a negative number, so it's positive. So here is our example. And I'll show you how to convert this so that we can figure out that it is -4. So we know that it's negative because the most significant bit is a 1, right? So we automatically know it's a negative number. And the way that we figure out that it is -4 is we first invert all of the bits. So all of the 1s become 0s. All of the 0s become 1s. So we end up with basically 0, 1, 1. And then the next step is to add 1. And then just like you did in grade school, so 1 plus 1 in binary, that's going to give you 1, 0, because you only have 2 digits, so you're going to have to carry it over. And then again, you get 1 plus 1. It's going to be 1, 0, so you put a 0, and then you get a 1 as a carry. And then 1 plus 0 is 1. So you get 1, 0, 0 in the end. And 1, 0, 0 is 4, right? So that's how you would negate. So you figure out what the negative representation is by negating it. And to negate it, you flip all the bits, add 1. So here's our flip all the bits and add 1. So here's 2, right? We're all comfortable with that this is 2. If we want to convert it to -2, flip all the bits, add 1. So we flipped all the bits here, and then now we have 1 plus 1, 0, 1, and then 1 plus 0 is 1. And this is now -2. So those of us seeing this for the first time, is it okay? I'm not hearing any response. Okay, so we're going to convert this back to +2. So again, in order to convert it, we flip all of the bits. So all of the 1s become 0s. And then the 0 becomes a 1. And then we add 1. So 1 plus 1 is 2. And then that gives us, so 2 in binary is 0, 1. Right? So we get a 0, the output, and then we have a 1 carry. And then 1 plus 0 is 1. And then 0, 0, 0, 0, 0. So that's flip and then add 1. So now this is 2. Is it better? So that's how you're going to go between the two. And if you're given a negative number, rather than use that equation from the previous slide, it is much simpler to convert it to the positive form. And then once you have it in the positive form, you know what the number is, and then you just know that it was negative before. Okay. So some examples. What's 0 if we were doing this?
All ones.
Yes. What's 0? 0. I mean, 0 is positive, right? So it's all zeros. Okay. -1. So again, easiest way to do this is start with 1 and then negate it. So 1 is a bunch of zeros and then a 1 at the end, right? I negate it. I have a bunch of 1s and a 0 at the end. I add 1. 0 plus 1 is 1. And I had all those 1s. So -1 is just all 1s. Right. So -5. I want you guys that are new to this, especially, to do this one on your own. And the process again is just make 5 first, and then convert it to a negative number. Are you two done over there? You got it? You hope? You can go over it together. They're going over it together. Okay, so I think you guys are mostly done. And if you aren't, we are going to go over this together. So first step is to make 5. What's 5? What's 5? Somebody please tell me 5.
0, 0, 1, 1, plus 0, 0, 1, 0.
No, just the 5, positive 5, positive 5.
Yeah, that's what I got.
Okay. You guys, what's your positive 5?
We got 0, 1, 0, 1.
0, 1, 0, 1 is positive 5. Because this is 1, this is 4. So 4 plus 1, this is 5. So the next step to make this negative 5 is invert it first, right? So 1, 0, 1, 0. And now that I've inverted, next step is add 1 to it, right? So plus 1. I have 1, 0, 1, 1. And then the other thing that we haven't talked about is if you want to make a signed number have more digits in it, you just copy the sign bits more times. So this is still negative 5, this is still negative 5, this is still negative 5. And then if this is still 5, this is still 5, this is still 5. So you just copy the sign bits if you want to make it more digits. Okay? So like we see a bunch of leading ones, and then the key is that we have 1, 0, 1, 1 at the end. And that is negative. All right. So 8, there's nothing new with 8, right? It's the positive numbers are exactly the same, 2's complements and unsigned. So 8 is 1, 0, 0, 0. Right? Yeah. All right. So the largest positive 32-bit number would be a leading 0 to indicate that it's positive, and all 1s. Okay? And the most negative 32-bit number is a leading 1, all 0s. Right. So sign extension, we talked about this just now. You just replicate the sign bits. So if it's, the other thing is if it's unsigned, you always just copy 0s. If it's signed, you copy the sign bits. So here we have signed examples. This is positive 2. If we want more digits, we just add 0s in the front. This is negative 2. We're a negative number, so if we want more digits, we copy the sign bits. More 1s are in front. Are we good with that? Okay. So the next thing is going beyond binary. We're going to cover another base. So hexadecimal, and apparently you forgot this, so you need to pay attention this time too, is base 16. Right? So we have more compact representation, and this is also very convenient because a lot of computers will use data sizes that are multiples of 4. And because of that, we can kind of just pack 4 bits together, make a hex digits. So here is our hex kind of alphabet. So in binary, we have 2 digits. In decimal, we have 10 digits. In hex, we have 16 digits. So we have 1 through 9 like normal, but then because we're out of our normal digits that we use because we have 10 fingers, right? We start going into the alphabets. So A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. So are we good with that? So in terms of some examples, we are going to, again, be using the same principle that we had before, except now our base is 16. So if we want to convert from hexadecimal to binary, we just have to kind of convert each one of these digits individually. So here we have E. So the 4 binary digits that would make up E are 1110. So we can see that goes here. Right? And next is C. C is 12. This is 12. A is 10. This is 10. 8 is 8. 6, 6, 4, 4, 2, 2, 0, 0. So if you convert it this way, this binary number is equal to that hexadecimal number. And you could double check this by computing the decimal representation of this and the decimal representation of this. And we're not going to do that because this is a very large number, right? But I will show you just to make sure that you know hex. This is 16 to the 0, 16 to the 1, 16 to the 2, 16 to the 3, 4, 5, 6, 7. So it's the same process. But now it's 16 to the 7 times 14 is the first component of this number. So it is a very large number, right? But for those of you new to this, is this okay? Okay. And then to convert from binary to hex, it's again very convenient to do this because now we're going to take the packs of 4 and compact them into 1 digit. So 1111, it's just going to be F. 1011, B, which is 11, and then 1000, 8, 1010 is A, 1010 again is A, 0010 is 2, 0011 is 3, 0001 is 1. And you don't have to memorize this table, right? You can just, I know that I have up to 9, and I know how to make a 4 digits binary number up to 9 very easily. And then I just have to remember that when I run out of my normal digits, then I start going into the alphabet. So after 9, 10 is A. And then again, I can make 10 through 15 with binary numbers from before. So you don't have to memorize the table. All right, so here is a checkpoint. So I want to go through this a little bit quickly. So just want to give you the code first. So the code for today is 391. So do answer the poll, but I think we can kind of just do this all as just someone volunteering. So anyone want to walk through how they're going to do this to get 25 in binary? Okay,
So should I walk up there?
however you want to do it.
Okay. So the first one is 16 because I remember F
is also 16 with all ones. Because the first digit is 2, second.
F is 15. Yeah, F is 15.
Okay, so that is 15. Because 2 plus, or 1 plus 2 plus 4 plus 8 is 15. And
Uh-huh.
for B, 1, there's only 1, and in the fourth part, or the fourth digit, the thousandth, is 2 to the third,
Uh-huh.
which is 8.
Uh-huh.
So 1 plus 8
Uh-huh.
is 9.
Uh-huh.
And then 2 to the fourth is 16.
Yeah.
So 16 plus 9 is 25. Which is the answer.
So basically, this one is 16. And the reason that we start with 16 is because if we go to the next one, this is 32, right? And 32 is too large. So that one does not work. So we don't include it. So we know our most significant bit is 2 to the 4, which is 16. And then you just have 9 here, right? So 16 plus 9, like you said, 25. Right? Okay, so again, let's go the other way. So can I have someone else? And remember, this is signed now. What number does this represent? Someone walk me through this.
Well, leading ones don't matter with signs, so you could start with the fourth. Would be like -8 plus 2 would be -6.
Okay, so let's do this kind of a little bit longer way. So you want to do it? First step is
Yeah, so I see that the leading bits are ones, so it's obviously not zero.
yeah, so we know it's negative.
So then there's a 1 in the 8th column, and then there's a 1 in the 2 column, so 8 plus 2 is 10, so -10.
Because remember what we have to do. So what do we have to do?
You have to invert.
Yeah, so first we invert everything. And then what's the next thing we do? Yep. So we add 1. So now 1, 1 gives me 0 with a carry. 1, 1, and then all my zeros. So you did the quick way, but this is the way that I was showing them before you came. So this is 4 plus 2, 6. So when we negated it, we found out that it's 6. So because we negated it, it's -6, right? All right, so here again is, so signed binary. Someone else to do this one? I need a volunteer. Right.
So we have 36. That we can,
You mean 32?
32, yeah.
Uh-huh.
And then that would be for 16. 8, 4, and then 2. At the very first goes with 1. The first
Yeah.
one.
So-
32 plus 8 is 40 plus 5, so 45.
So the way I do it is I have this kind of more or less memorized. This is 13. This will cooperate. This is 13. and then 32 plus 13, like you mentioned, 40. Right? Okay, so now unsigned but fixed point representation. So can someone walk me through this one? I need a volunteer. Someone from over there, please. Yeah, I don't want to call on anyone. Let's walk through this together. Someone to lead. You want to lead?
Yeah, sure. So since it's 0.75, it's the 0.5, like 2 to the negative
Uh-huh.
1 and or
Uh-huh.
yeah, and then the second one, so it'd be 0.11, so it's either A or
Yeah,
B.
so we know that this is 0.5 because it's 2 to the negative 1, and then this is 2 to the negative 2, 0.25,
So it'd be
which
A.
is 0.75. So like you said, we know that we need 1 after the decimal. So what about before the decimal?
So you'd add like 32 and 1, so it'd be A.
So this is 32. This is 1. Okay. Right? Okay. All right. This is you. What's my process here?
For each individual
Huh?
impacts of the binary.
Okay, so what is A? Tell me in decimal first.
That's right.
Yep, 10. So then I just need to convert 10 to binary.
One, zero, 1, 0.
Yep. So this works, this works.
Two, WD.
This works. This works, this works. Yeah. So everyone over there follow this too? Okay. So let's see. We still have some time and we do need to get through this. So performing addition in binary and any base is exactly how you learned it in grade school. It's just now you're carrying once you reach a different threshold because you have a different number of digits. And for us in binary, that threshold is 2 because we only have 2 digits. So we can represent 0 and 1. And once we hit 2, we gotta go to the next digit. So here we have our example. We have 1 plus 0. We get 1, right? And we have a 0 as our carry because we didn't need it, right? And then here 1 plus 1, we get a 0, and we have a 1 as a carry up here. And now we have 1 plus 1 plus 1, which is now 1, 1, right? And then 1 plus 0 plus 0, 1, no carry, 0, 0, 0, 0, 0, 0, 0, 0, right? So just like grade school,
Sometimes you carry one still.
you would carry however much you needed to carry. So like if I have in hex, I have 16, but well, it wouldn't be 16. Let's call it. Let's do F plus let's do 5. F plus 5, right? So this is actually 20, right? So we get how much down here? What's my base? 16, right?
Yeah.
So 20 minus 4. So I have 4 here, carry a 1. And now basically 1 plus 0 is 1. So then I have 16 plus 4, 20. So you keep the leftover and then you just carry the 16, essentially. And so like in decimal, we're always carrying a 10. In binary, we're carrying a 2.
Oh, okay.
So in decimal, you carry the 10, and in binary, you carry the 2, so that's, you carry 16.
Yeah, a 16. A 16. That's why, because F plus 5 is 20. So we have leftover a 4, and we carry a 16. But in hex, it's really a 1, right? So same thing with binary, like whenever we carry, it's a 1, but really it's a 2. And same thing with decimal, we always carry a 1 to go to the next, but really it's a 10.
Okay.
All right, so here are some integer addition examples. So 5 plus 1. We're comfortable with 5 and 1 here, conversion. And then if we're going to do the computes, 1 plus 1 is 1 plus 1, 0, 1, right?
Yeah.
So we have a carry of 1. So 0, 1, 1, 0, 0 gives me just 1, 0, 1, 1, 1, 0 is just 1, right? And then 0, 0, 0 is 0. And then we can always check our answer, right? This is 4, this is 2, that is indeed 6. Right? So another thing is we can do addition of negative numbers. And just, I'm not going to go through the process of explaining why the 2's complement works. But just know that you just do the addition the same way. Right, we have 7, and this is negative 5. We can confirm that's negative 5 by just negating it. So 0, 1, 0, 0, and then plus 1, 0, 1, 0, 1, right? That's 5. So we're just going to do this addition the same way that we do the normal addition. So 1 plus 1 is 0, 1, right? So we carry the 1. We have a 0 at the bottom. 1, 1, 1 is 1, carry the 1. 1, 1 is 0, carry the 1. And then again, 1, 1 is 0, carry the 1. And I will tell you how to know what to do with this. In this case, it's just thrown out. But later on, I'll tell you how to handle this with these sign numbers. For now, we can just check that down here, this is 2, right? So we know our answer is 2, and indeed 7 plus negative 5 is 2, right? So we'll continue this on Wednesday, and we'll also have a guest lecture for the last half of class on Wednesday. But if again, all the cancels, we'll continue doing this. Okay? And just to make sure, if you have not answered the poll everywhere, the code is, what is it? 391? What was it? Yeah, 391. So do answer that in case you didn't. And I forgot to do poll everywhere on Wednesday and Friday last week. If that ever happens, do just tell me that I need to do the poll. So basically Wednesday and Friday, I'll just give everyone participation. That's, just let me know if I forget. Okay.